Everything in this world is made up of tiny particles. The amount of particles that go into making different products may vary, but every object will have atoms as its smallest building block. The structure of an atom. Everything in this world is made up of tiny particles, right? The amount of particles that go into making different products may vary, but every object will have atoms as its smallest building block. So, what is an atom? So now let's fast forward to the late 1800s when things changed. When Sir J.J. Thomson accidentally discovered the electron. That happened while he was conducting experiments using a cathode ray tube. Now, before going further, first let me tell you what a cathode ray tube is. A cathode ray tube is a vacuum sealed tube that does not allow air to enter it. Now, inside the tube, on one side, a cathode is placed, and on the other side, an anode is placed. Okay, wait, so some new terms, is it? Now, before you start wondering, the cathode is a negatively charged conductor and the anode is a positively charged conductor. And the anode has a small hole and its opposite wall of the tube is coated with fluorescent material from the inside. Got it? Back to Thomson's experiment. So, in a dark room, when an electric current is passed through a gas at high voltage and low pressure, he found out that a stream of minute particles is let out by the cathode, and the small hole on the anode allowed this beam of light to pass through it. And when this beam struck the wall coated with fluorescent material, it started to glow. Wow, that's fascinating, wouldn't you say? From this, he decided that these particles must have come from somewhere within the atom, and that Dalton was incorrect in stating that atoms cannot be further divided into smaller pieces. Now let's take a closer look at what happened inside the cathode ray tube. When a high electric current is applied, the electrical energy pushes out some of the electrons from the gas. These fast-moving electrons form cathode rays. Well, Thomson never set out to discover electrons with this cathode ray tube experiment, but while running this experiment, he stumbled upon this discovery. And that's why no one called it an electron beam back then. Instead, what flowed out of the cathode and traveled towards the anode was called a cathode ray. So this is how Sir J.J. Thomson discovered electrons. So that was all about how electrons made a grand entry in the world of science. Now let's look at how protons came to the fore. In 1886, E. Goldstein, while performing some experiments with a discharge tube containing perforated cathode, observed that when the cathode rays are traveling from the cathode to the anode, there are some other luminous waves which travel from the anode to the cathode, and he called these canal rays. Why that name, you wonder? Any guesses? Simple. Since these rays passed through the holes of the cathode, he named them canal rays. With his experiments, he found that these rays are made up of another subatomic particle later labeled as proton by Rutherford. These rays are also called as anode rays as they emerge from the anode and they travel towards the cathode. So it became necessary to find out how these electrons and protons were arranged inside the atom. But do remember that the third subatomic particle, neutron, had not been discovered at that time. We are talking about the late 1800s when only electrons and protons had been discovered. So all the atomic models that were studied only contained protons and electrons. The first attempt to describe the internal structure of an atom was done by Sir J.J. Thomson. He went one step further and proposed the model of an atom to be similar to that of, you will never guess what I'm going to say. He suggested that it was similar to that of a Christmas pudding. He stated that negatively charged electrons needed a positive charge to balance them out. So he determined that they were surrounded by positively charged material. Now this came to be known as the plum pudding model of the atom. Have you tasted it? I love plum pudding. Anyways, moving on. This basically means that the negatively charged plums were surrounded by positively charged pudding. We can also think of a watermelon. The positive charge in the atom is spread over like the red edible part, while the electrons are studded in the positively charged sphere like the seeds in a watermelon. Now, Thomson made two observations. First, an atom consists of a positively charged sphere and the electrons are embedded in it. Second, the negative and the positive charges are equal in magnitude. So the atom as a whole is electrically neutral. Now the experiments didn't stop there. A few years later, Ernest Rutherford, one of Thomson's students, ran some tests on Thomson's plum pudding model. In his experiment, Rutherford fired a beam of positively charged particles called alpha particles at a very thin sheet of gold foil. Now you're probably going to ask, what are alpha particles? Alpha particle is a positively charged particle having 2 units of positive charge and 4 units of mass. It is actually a helium ion with a +2 charge. Alpha particles are emitted by radioactive elements like radium and polonium. The fast-moving alpha particles have a considerable amount of energy. They can penetrate through matter to some extent. Now, talking about the gold foil reminds me of a thin layer of silver sheet on Indian sweets. You must have seen it, right? Yes, it is edible too, but you may also know that it is very fragile. So thin that it breaks even if you place a finger on it. Now, this gold foil was as thin as that. Getting back to the Rutherford experiment. He placed such a thin foil at the center of a circular detector. Now, what was the detector used for? The detector would flash if an alpha particle hit it. These alpha particles had so much mass that Rutherford was mighty sure that when he would fire them, all of them would pass right through the gold foil and hit the detecting screen on the other side. But here comes the twist. When Rutherford fired the alpha beam, something strange happened. This is what he observed. First, most of the fast-moving alpha particles passed straight through the gold foil. Second, some of the alpha particles were deflected by the foil at small angles. Third, 1 out of every 12,000 particles appeared to rebound. In simple words, some of the alpha particles went through and hit the detector. But Rutherford noticed that the detector was flashing from various angles. So he realized that some of the particles were deflected by the gold foil and hit the detector in different locations. Some even directly went back to the path they came from. So this is what Rutherford had to say. This result was almost as incredible as if you fire a 15-inch shell at a piece of tissue paper and it comes back and hits you. So the present concept of an atom that we all know is given by Niels Bohr. Let us study the postulates of Bohr's atomic model in detail. Here is the first one. An atom is made up of 3 particles. They are electrons, protons, neutrons. Electrons have negative charge, protons are positively charged, and neutrons are neutral in nature. The number of protons and electrons in each atom is equal. This makes the atom electrically neutral. Second, protons and neutrons are present at the center of an atom, which is known as the nucleus. The nucleus is positively charged due to the presence of protons. Third, electrons revolve around the nucleus in a fixed circular path called an energy level or a shell. Now we can represent these energy levels either by letters like K, L, M, N, and so on. That is, the first orbit is denoted by the letter K, the second orbit by the letter L, third by M, and so on. Or they can also be denoted by numbers like 1, 2, 3, 4, etc. The energy levels are counted from the center, moving outwards. TutorMate, for more amazing video lectures, download the free app on the Apple App Store or the Google Play Store.